Deep in the distant universe lies a cosmic giant Ton 618, one of the largest black holes ever discovered. Its mass defies imagination, and its light has travelled billions of years to reach us. Tonight we'll explore what makes this monster so extraordinary. If you enjoy these journeys through the cosmos, please subscribe and share, and tell us in the comments, what would you ask if you could look straight into a black hole? Thank you for watching. Now, let's begin. The scene is a universe much younger than the one known in the present day, a cosmos that has expanded for only around 3 billion years since the first light breaks free after the hot early phase. Matter is no longer a nearly uniform mist, and large-scale patterns now stand out across hundreds of millions of light years. But the overall glow of the cosmic microwave background still carries more warmth than it does in the nearby universe. At this epoch, the average density of matter and radiation is higher, structures grow more quickly, and the night sky, as it would appear from a suitable location, holds a greater number of intensely bright active galaxies than in later times. Gravity has had enough time to pull gas, dark matter and stars into filaments and dense knots, giving rise to a busy era for the growth of massive galaxies and the black holes that sit in their centres. In this distant time, one of the many active galactic nuclei is the source that will later be catalogued under the name Ton 618. But in its own era, it is simply one among many quasars that radiate strongly across the observable spectrum. The expansion rate of the universe at this redshift is different from the present one, and astronomical distances are described with care since several different measures are in use. The light that leaves Ton 618 at this stage of cosmic history will take roughly 10 and a bit billion years to arrive at the location of Earth in the present day. Yet the actual separation between the quasar and the modern Milky Way, when expressed as a co-moving distance that follows the expansion, is on the order of tens of billions of light years. These distinctions arise naturally in an expanding space where photons travel along curved paths in space-time, and the scale of the cosmos steadily increases while they are in flight. Astronomers reconstruct this distant time not by direct travel, but by reading the information encoded in the faint signals that reach large telescopes. Each photon arriving from the direction of Ton 618 carries with it a record of conditions long ago shifted to longer wavelengths by the stretching of space itself. Shorter wavelength ultraviolet light can arrive as visible light, or even as near-infrared light, and spectral lines that begin at well-known laboratory wavelengths are displaced by factors of more than 3. This shift, when measured carefully, gives the redshift value of about 2.219 that is associated with Ton 618, and that number in turn links the quasar to a specific era in the history of structure formation. In such an era, quasars are more common than they are in the nearby universe. Many galaxies hold central black holes that are actively accreting gas, converting gravitational energy into radiation with a high efficiency. The combined glow of this population makes a significant contribution to the high-energy background of the cosmos, and the environments around these active nuclei are places where gas is heated, ionized, and driven into large-scale motions. Star formation in massive galaxies is also vigorous at this time. Cold gas flows along cosmic filaments into deep gravitational wells where it can cool, condense and fragment into dense clouds that form new stars. The rate of star birth per unit volume of the universe is higher than it is in later, more quiescent ages, and chemical elements heavier than hydrogen and helium are being created and mixed into the interstellar and intergalactic medium by supernova explosions and stellar winds. Against this backdrop, Ton 618 is notable for its extraordinary luminosity. Even among the bright quasars of this redshift, it stands out as one of the most radiant known with energy output that exceeds that of ordinary galaxies by many orders of magnitude. The source appears point-like in most observations because its great distance compresses even very large physical scales into a tiny angle on the sky. Yet behind that point-like appearance lies a complex and layered physical system governed by gravity radiation and the flow of gas. In this opening view, the focus remains on the broad setting rather than on those inner components. The key idea is that TON 618 does not sit alone in empty space. It is part of a population that traces peaks in the matter distribution at a time when the universe is especially efficient at building large structures. Its light serves as a probe of the medium through which it travels, and its existence provides evidence that black holes, with masses of many billions of solar masses, already exist when the universe is still relatively young. Reaching such masses requires prolonged or highly efficient accretion, or the assembly of several smaller black holes through mergers, and in either case the presence of TON 618 challenges models of how quickly such objects can grow. Observers approach this epoch armed with models of cosmic expansion, structure formation, and radiative transfer, but they also allow the data to guide revisions of those models, since quasars like TON 618 can reveal gaps in current understanding. In the present era, large surveys on the ground and in space scan broad regions of the sky to find distant quasars, measuring their redshifts and brightnesses and building up statistical samples. Among these, TON 618 occupies the bright end of the distribution, and its particular combination of redshift luminosity and spectral features marks it as a valuable laboratory for studying both the central engine and the wider cosmic environment. As the narrative of this film settles into this distant epoch, it takes the time to let this context become clear. A young universe, dense and active, threaded with a cosmic web that channels matter into deep potential wells, and punctuated by brilliant quasars whose light crosses billions of years to reach modern detectors. Within that landscape, TON 618 shines steadily, a single bright point that encodes in its spectrum the conditions of a time when the universe is busier, hotter and more crowded with forming structures than the quieter cosmos more familiar from local observations. The large-scale environment around TON 618 sits within the interconnected network of matter that cosmologists call the cosmic web, a pattern that arises naturally when tiny initial irregularities in the early universe grow under the influence of gravity. Over hundreds of millions of years, regions that begin slightly denser than average attract more material, while slightly emptier regions give up matter to their surroundings, and this simple process gradually amplifies the contrast between rich and poor zones. Simulations that follow dark matter and gas together show the emergence of long, gently curved filaments that span tens to hundreds of millions of light-years, converging into dense knots where several strands meet. Between these filaments lie wide, underdense voids where the density of matter falls below the cosmic mean, and structure grows more slowly. The result is a three-dimensional pattern that resembles a network of threads and intersections, rather than a random sprinkling of galaxies, and it is along these threads and at these junctions that massive halos form. TON 618 belongs to one such deep halo, at an intersection of the web, a place where gravity has gathered a great deal of dark matter and gas by the time the universe reaches the redshift associated with this quasar. Although observers cannot map every detail of the web around TON 618, directly comparisons with simulations and with surveys of galaxies at similar redshifts suggest that the quasar likely inhabits a dense region, perhaps the core of a forming cluster of galaxies. In these environments, the local matter density exceeds the average by a significant factor, and the rate at which gas flows along filaments into the central halo can be high enough to sustain both intense star formation in galaxies and substantial feeding of central black holes. Filaments act as highways for cold gas, which can stream inward without being shock heated to very high temperatures, especially at early times when the masses of halos and the properties of the intergalactic medium allow such flows to penetrate deeply. As the gas moves inward along these preferred directions, it can fragment and form galaxies along the filament, leading to alignments and chains of objects that trace the underlying dark matter structure. Around a massive halo like the one that holds Ton 618, multiple filaments may arrive from different directions, bringing in both dark matter and baryonic gas over extended periods. These inflows build up the total mass of the halo and supply fresh material to its inner regions, where it can eventually cool further and participate in star formation and black hole growth. In the outskirts of such a halo, the gas distribution is not uniform, but instead shows clumps, streams, and diffuse components that respond to both gravity and the pressure of radiation and hot plasma. Some of this gas has never been inside galaxies and retains a relatively simple chemical composition dominated by hydrogen and helium, while other portions have been cycled through galaxies and carry higher abundances of oxygen, carbon, and other products of stellar nucleosynthesis. The mix of these components reflects the cumulative history of inflow star formation feedback from stellar winds and supernova and outflows driven by earlier episodes of nuclear activity. Gravitational potential wells of this scale can exceed masses of many trillions of solar masses when dark matter and baryonic matter are combined, although current observations do not yet provide a precise direct measurement for the halo of Ton 618. Instead, the likely mass range is inferred statistically by comparing the space density of such luminous quasars with the predicted abundance of massive halos in cosmological models. The reasoning is that very bright active nuclei tend to reside in relatively rare high-mass halos because only those environments have enough gas supply and depth of potential to sustain extreme accretion over extended times. Measurements of how quasars cluster with galaxies and with one another also provide clues, since tighter clustering points to residence in more massive halos. At the redshift of Ton 618, analyses of quasar clustering indicate that many luminous objects inhabit halos similar to those that later evolve into rich clusters of galaxies in the nearby universe. Thus, while the exact halo mass of Ton 618 remains uncertain, it is reasonable within current knowledge to place it among the most massive structures that exist at that epoch. Within this web-based context, the light that eventually reaches telescopes from Ton 618 does not arise in isolation, but is associated with the deep potential well located at a node of the cosmic web where several filaments converge. The surrounding space is populated by other forming galaxies, some of which may be visible in deep imaging as faint companions or as overdensities of galaxies near the quasar sightline. Others may remain below current detection thresholds, contributing mass and gas without yet producing enough light to stand out individually. In any case, the density of structure in this region is higher than in the average field, and the combined gravity of the halo and its neighbours shapes the motions of gas and galaxies on scales of hundreds of thousands to millions of light years. Gas falling into the halo can shock heat and radiate, establishing a tenuous but extended atmosphere that surrounds the denser inner components. At the same time, feedback from forming stars and from active nuclei within the halo can drive winds and outflows that propagate back into the web, enriching the inflowing gas with heavier elements and altering its temperature and ionization state. These exchanges between inflow and outflow between filaments and halos are part of a continuous cycle that gradually builds up the complex environment seen around massive structures in the later universe. The cosmic web not only channels matter toward TON 618, but also provides a backdrop against which its properties can be interpreted, linking the presence of such an extreme quasar to the densest peaks in the matter distribution at this cosmic time. Between the distant quasar and the location of present-day observers stretches a long path through intergalactic space, a medium that is not empty, but filled with diffuse gas that leaves a clear imprint on the light of TON 618. Photons that set out from the quasar's bright central regions pass through many distinct structures before they arrive, and each encounter with gas along the way modifies the spectrum in a small but measurable way. When the light finally reaches large telescopes, it carries a record of this journey encoded as a forest of absorption lines that astronomers call the Lyman alpha forest. This forest arises primarily from neutral hydrogen in the intergalactic medium, which absorbs photons at a specific ultraviolet wavelength, corresponding to the Lyman alpha transition. Because of the expansion of the universe, each cloud or filament of hydrogen along the line of sight imprints its absorption at a slightly different observed wavelength depending on its redshift, so that what begins as a single intrinsic wavelength becomes a series of closely spaced features in the observed spectrum. The result is a dense pattern of dips blueward of the quasar's own Lyman alpha emission line, each dip corresponding to a region of gas at a particular distance and cosmic time. At the redshift of TON 618, the intergalactic medium is mostly ionized, meaning that much of the hydrogen is separated into protons and electrons by the combined action of ultraviolet radiation from galaxies and quasars. However, a small fraction of hydrogen remains neutral, and this fraction is enough to create substantial absorption along the line of sight. In denser regions where the gas collects into filaments and sheets associated with the cosmic web, the neutral fraction and column density increase, producing stronger and sometimes saturated Lyman alpha lines. In lower density voids, the absorption is weaker, resulting in shallow features or nearly transparent stretches of spectrum. By modelling the shapes and distributions of these lines, astronomers infer the temperature density and ionization state of the intergalactic gas at different redshifts, building a picture of how matter is arranged on scales much larger than individual galaxies. The line of sight to a bright high redshift quasar like TON 618 is particularly valuable for such studies because its intense ultraviolet and optical continuum provides a bright background against which even modest amounts of absorbing gas stand out clearly. In addition to simple Lyman alpha lines, the spectrum along this path often includes systems with higher column densities that produce not only Lyman alpha absorption, but also additional transitions such as higher order Lyman series lines, and in some cases a sharp drop in flux at wavelengths shorter than the Lyman limit of hydrogen. These systems, known as Lyman limit systems or damped Lyman alpha systems, depending on their column density trace more substantial concentrations of gas, some of which may be associated with forming galaxies or their extended gaseous envelopes. Metal lines from elements such as carbon, silicon and oxygen also appear in many of these systems, indicating that the intergalactic medium is not entirely pristine, but has been enriched by material expelled from galaxies through winds and outflows. Along the line of sight to TON 618, such systems mark locations where past generations of stars have already processed hydrogen and helium into heavier elements and returned them to the surrounding medium. The distribution and strength of metal lines provide clues about how far galactic feedback reaches into intergalactic space, and how uniformly the products of stellar evolution are mixed. Closer in redshift to the quasar itself, the intense radiation field from TON 618 begins to influence the properties of the gas. In the immediate vicinity along the line of sight, the strong ionizing flux reduces the neutral hydrogen fraction, producing what is known as a proximity zone. In this region, the Lyman alpha forest becomes more transparent than it would be if the quasar were absent, because the quasar's photons further ionize the gas, on top of the ionization maintained by the more general background radiation from other sources. The size and structure of this proximity zone depend on the quasar's luminosity emission history and the density of the surrounding medium. Although the exact details for TON 618 are constrained by the quality and coverage of current spectral observations, the general concept remains that its radiation carves out a slightly clearer region along the line of sight sitting at the far end of a long sequence of absorbing structures. Throughout most of this intergalactic path, the gas remains at relatively low density compared with galactic environments, and its temperature typically lies in a range of tens of thousands of degrees, set by the balance between photoheating from ultraviolet radiation and cooling through expansion and line emission. The hydrogen and helium in these regions respond smoothly to changes in the radiation field and density, so that the Lyman alpha forest traces a continuous field rather than a set of discrete cloud-like objects. Numerical simulations confirm that many of the absorption features correspond to gently varying over densities in filaments and sheets of the cosmic web, with only the strongest systems arising from more compact structures. For TON 618, the line of sight provides a representative cross-section through this environment at redshifts between the quasar and the present day, allowing studies not only of the conditions near the quasar redshift, but also of the evolution of the intergalactic medium as a function of distance. By measuring how the average transmitted flux and the distribution of line strengths change with redshift, along this path observers track how the ionizing background and gas density evolve over billions of years of cosmic time. Even though the primary focus of interest in TON 618 often rests on its central black hole and luminous accretion disk, this intergalactic component remains an essential part of the full picture, because it both shapes the observed spectrum and records the state of the universe through which the light travels. The path is not a simple featureless corridor, but a structured medium that interacts with the photons in a way that is sensitive to temperature, density, and ionization. In calm, steady language, the journey of light from TON 618 can be pictured as a passage through a series of mildly over-dense and under-dense regions, each region leaving its own small signature on the spectrum. Collectively, these signatures encode the history of gas falling into the web, being heated and ionized, being enriched by galaxies, and becoming part of the broader environment that surrounds the massive structures at redshift around 2.2. By the time the light reaches large telescopes, the original sharp spectral features emitted by the quasar carry this overlay of intergalactic absorption, and it is through careful analysis and modelling that astronomers separate the intrinsic properties of TON 618 from the imprints of the medium that lies in front of it. In this way, the line of sight acts both as a filter and as a measurement tool, allowing the same data to inform studies of both the distant quasar and the intervening intergalactic medium. Around the massive halo that hosts TON 618 lies a broad region of gas known as the circumgalactic medium, an extended atmosphere that reaches far beyond the visible parts of any embedded galaxy and blends gradually into the intergalactic medium. This circumgalactic medium is not a sharp shell, but a wide diffuse volume that stretches over hundreds of thousands of light-years, filling the space between satellite galaxies' filaments and the deeper interior of the main halo. It contains gas at a range of temperatures and densities from relatively cool dense clumps and streams to warm and hot more diffuse phases that are heated by gravitational infill shocks and radiation. At the redshift of TON 618, This circumgalactic region plays a crucial role in regulating how material flows into the inner parts of the halo, and how energy and metals flow out. Gas arriving along cosmic filaments does not halt abruptly at the notional edge of the halo, but continues inward, sometimes forming coherent streams that maintain lower temperatures and higher densities than the surrounding medium. These cold or warm streams can thread the circumgalactic medium, delivering fuel toward the inner tens of thousands of light years, where it may eventually join the interstellar medium of galaxies. At the same time, activity within those galaxies, including both star formation and feedback from active nuclei, can send material back outward, enriching the circumgalactic medium with heavier elements and injecting energy that changes its structure. In numerical simulations, halos of this mass and redshift show circumgalactic media that are rich in structure, with filaments, clouds, and turbulent flows superposed on a more nearly spherical hot diffuse component, photon 618. Current observations do not resolve all of these details, but indirect evidence from absorption and emission features suggests the presence of a complex multi-phase circumgalactic medium, similar in spirit to that seen in other massive halos. The gas is partly ionized with hydrogen and helium in various states depending on local density and exposure to radiation, and it carries a mixture of metals produced in earlier generations of stars. The circumgalactic medium around the host halo of TON 618 is bathed in strong radiation from the quasar itself, in addition to the more general background produced by other galaxies and active nuclei. This intense local field tends to push the ionization state of the gas toward higher levels, especially within a few 100,000 light-years of the central source. Hydrogen that might otherwise remain partially neutral becomes more fully ionized, and metals shift to higher ionization stages. As a result, when the gas is probed in absorption against background sources or in emission, it often reveals strong high ionization lines that reflect both the intensity and hardness of the quasar radiation. The structure of the circumgalactic medium is also influenced by the gravitational potential of the halo. Gas that has fallen into the halo and been shock-heated can settle into a roughly hydrostatic configuration, where thermal pressure and to some extent non-thermal processes such as turbulence and magnetic fields partially support it against further collapse. In massive halos, the characteristic temperature of this hot component can reach tens of millions of degrees, sufficient to keep hydrogen fully ionized and to produce emission in soft X-rays and extreme ultraviolet bands. Against this hot background, cooler clouds and streams stand out as overdense features that can radiatively cool more rapidly, forming long-lived structures if they are not destroyed by instabilities or mixing. These cooler components contribute strongly to ultraviolet and optical emission lines when illuminated by the quasar, and they provide efficient pathways for gas to radiate away energy and lose angular momentum as it drifts inward. Observationally, the circumgalactic medium around quasars at similar redshifts is often studied through absorption, seen in the spectra of background galaxies or quasars, or through extended emission lines that trace gas on scales larger than the host galaxy. For a source as luminous as TON 618, the central continuum and line emission can dominate the view, making it challenging to separate the faint glow of the circumgalactic gas. However, careful analysis of the profiles and spatial distribution of certain lines reveals hints of extended ionized gas that likely belongs to the circumgalactic medium rather than to the compact inner regions. The velocities of this gas inferred from Doppler shifts indicate motions of hundreds of kilometers per second, reflecting both gravitational infall toward the center and outflows driven by energy input from the quasar and from any associated star formation. Within this medium, the balance between inflowing and outflowing material is not static. Gas arriving along filaments brings in relatively low metallicity material from the intergalactic medium, while outflows carry higher metallicity gas from galaxies back into the halo. Over time, this circulation raises the overall metal content of the circumgalactic medium, especially near the halo center, while still allowing for pockets of more pristine gas in the outskirts. At the epoch of TON 618, this process is already well underway, so the circumgalactic medium likely contains a mix of chemical abundances with gradients that reflect the history of star formation and feedback in the system. The density of the circumgalactic gas decreases with distance from the center of the halo, so that the innermost regions on scales of tens of thousands of light years can reach densities high enough for efficient cooling and emission, while the outermost regions merge gradually into the lower density intergalactic medium. The transition is not sharp, and the detailed profile depends on the interplay of accretion cooling feedback and the growth of the dark matter halo. For TON 618, large-scale modelling suggests that the halo sits near the high mass end of the distribution, which implies a substantial reservoir of circumgalactic gas, capable of sustaining both central accretion and extended star formation over significant periods. The presence of a bright quasar also means that parts of the circumgalactic medium are likely out of simple thermal equilibrium, with regions near the radiation cones of the nucleus being more strongly ionized and heated than regions shielded by dense gas or lying outside the primary beams. This leads to anisotropies in ionization and temperature that, while difficult to map fully in a single object, are predicted by theoretical models and supported by statistical studies of quasar environments. In this calm, slowly paced view, the circumgalactic medium around TON 618 appears as a vast layered atmosphere that mediates the exchange of matter and energy between the larger scale cosmic web and the inner structures of the halo. It is neither purely inflowing nor purely outflowing, but rather a dynamic mixture of gas at different temperatures and histories. Every photon that passes through this region, on its way from the central source to distant observers, encounters some part of this medium, and the cumulative effect is recorded in subtle shifts and strengths of spectral lines. Although the immediate interest in TON 618 often centers on its extraordinary central engine, the circumgalactic medium remains an essential component of the system, setting the boundary conditions for how gas can reach the inner regions, and how the power generated near the center can propagate outward. Embedded within the circumgalactic medium around TON 618 is an especially striking structure, an extended Lyman alpha emitting nebula, a vast volume of hydrogen gas that glows because it is exposed to the intense ultraviolet radiation from the quasar. Lyman alpha emission arises when an electron in a hydrogen atom falls from the second energy level to the ground state, releasing a photon with a specific energy. In the rest frame of the gas, this corresponds to a well-defined ultraviolet wavelength, but in the observed frame for a source at a redshift of about 2.2, the line is shifted into the optical range, making it accessible to ground-based telescopes equipped with sensitive spectrographs and imaging instruments. Around TON 618 observations reveal that the Lyman alpha emission does not come only from the compact inner regions near the nucleus, but also from a much larger scale nebula that extends over distances measured in tens or even hundreds of thousands of light years. This nebula represents a luminous tracer of the otherwise invisible circumgalactic hydrogen, allowing astronomers to map out part of the gaseous halo in emission, rather than solely in absorption. The gas in this nebula is predominantly ionized by the quasar's powerful radiation field. Photons with energies above the ionization threshold of hydrogen remove electrons from atoms, creating a plasma of protons and free electrons. As electrons recombine with protons and cascade down through the allowed energy levels, they produce line emission, including Lyman alpha. Because the quasar is extremely luminous, its radiation can ionize gas far beyond the boundaries of the host galaxy, and recombination in this extended region can sustain a large diffuse glow. The surface brightness of the nebula declines with distance from the center, reflecting both geometric dilution of the radiation and variations in gas density. But sensitive observations can still pick up the faint light in regions where the gas is relatively dense, or where its distribution aligns with the line of sight in a favorable way. In addition to simple recombination, resonance scattering plays an important role in shaping the appearance of the Lyman alpha nebula. Lyman alpha photons interact strongly with neutral hydrogen, undergoing repeated absorption and re-emission events that cause them to scatter many times before escaping the gas. Even in predominantly ionized plasma, small fractions of neutral hydrogen can be enough to trap Lyman alpha radiation, temporarily lengthening its path and altering its spatial and spectral distribution. This resonant process tends to spread the emission over a wider area, making the nebula appear more extended than it would if the photons travelled in straight lines. It also broadens and reshapes the line profile, since each scattering event can slightly shift the frequency of the photon, especially when the gas has bulk motions or turbulence. For TON 618, the detailed kinematics and structure of the Lyman alpha nebula depend on the velocity field and density distribution within the circumgalactic medium, but even without a complete map, it is clear that the nebula is large and significant, marking a substantial reservoir of hydrogen that has been lit up by the central source. The presence of such an extensive nebula indicates that plenty of gas remains available in the halo at this epoch, despite ongoing star formation and black hole accretion. Some of this gas may be flowing inward along filaments, while other parts may be material that has been pushed out from inner regions by winds or outflows and is now mixing with the halo. The Lyman alpha emission, however, does not itself distinguish between inflow and outflow. It primarily reveals where the gas is present and illuminated. To disentangle motions, astronomers examine small shifts in the line centroid and changes in its shape across different regions of the nebula. Modest redshifts or blue shifts relative to the systemic velocity of the quasar can indicate net motion away from or toward the observer, while asymmetries in the profile can hint at radiative transfer effects in moving media. For TON 618, constraints on these patterns depend on the quality and spatial resolution of the data, so interpretations remain cautious, but the broader picture of a dynamic glowing halo remains secure. The Lyman alpha nebula also carries information about the chemical state of the gas. Although hydrogen dominates observations, sometimes detect faint emission or absorption lines from heavier elements superposed on or near the Lyman alpha feature. The presence of these metals indicates enrichment by earlier generations of stars, either within the host system or in nearby galaxies, whose winds have carried processed material into the halo. The relative strengths of metal lines when measurable help to constrain the metallicity of the nebula, and thus the degree to which it has participated in the cycle of star formation and feedback. In the case of TON 618, the nebula is likely not chemically pristine, but its exact metallicity remains subject to measurement uncertainties. Nonetheless, the detection of extended Lyman alpha emission on these scales is consistent with theoretical expectations that massive halos at this redshift contain large, partially enriched gas reservoirs. Another important aspect of the Lyman alpha nebula is its geometry. In some quasar systems, extended emission appears more concentrated along certain directions, possibly reflecting anisotropies in the ionizing radiation field, such as the presence of cones where radiation escapes more easily, or the influence of large-scale structures like filaments. Dust and dense gas near the nucleus can block radiation along some lines of sight, while leaving others relatively unobscured, creating an uneven illumination pattern in the surrounding halo. If similar effects operate around TON 618, they could cause the Lyman Alpha Nebula to appear brighter and more extended in some directions than others. Observations that resolve the nebula spatially can test for such asymmetries, but even without a complete three-dimensional picture, it is reasonable to expect that the structure is not perfectly spherical. The quasar's radiation field combined with the irregular distribution of gas naturally leads to complex shapes. From the perspective of the narrative, the Lyman Alpha Nebula can be seen as a quiet, widespread glow that marks the boundary region where the influence of the quasar becomes manifest in emission rather than only in its gravity. It forms a luminous envelope around the more compact core of the system, tracing where hydrogen in the circumgalactic medium has been excited enough to shine. Its existence shows that the bright central engine is not an isolated point, but is energetically coupled to gas on much larger scales, transforming parts of the halo into a giant, softly glowing structure. At the same time, it serves as a bridge between the broad, diffuse circumgalactic medium and the more concentrated regions closer in where densities rise and other emission lines become more prominent. The host galaxy of TON 618 sits deeply buried beneath the glare of the quasar so intense that in most observations the galaxy itself does not stand out as a separate structure. Instead, the light from the central active nucleus floods the image, making the source appear almost point-like even in powerful telescopes. To study the underlying galaxy, astronomers rely on indirect methods and on comparisons with other quasars at similar redshifts whose hosts can be observed more clearly. They use techniques that attempt to subtract the point spread function of the bright nucleus from high-resolution images, leaving behind any extended emission that might be associated with stars gas or dust. For TON 618, such efforts are challenging, and the results so far provide only broad constraints rather than a detailed portrait. Even so, the combination of theoretical expectations and limited observational hints points to a massive galaxy that has already assembled a large stellar population by the time the universe reaches this stage. The typical hosts of luminous quasars at redshift around 2 often show stellar masses of hundreds of billions of solar masses, substantial bulge like components and signs of vigorous star formation. It is reasonable within current understanding to place the host of TON 618 in a similar category, although its precise mass morphology and star formation rate remain uncertain. In this picture, the galaxy likely contains a dense central region where stars are packed more tightly than in ordinary spiral disks, forming a spheroid or bulge that surrounds the central black hole on kiloparsec scales. Beyond this bulge, there may be an extended stellar component that could resemble a thick disk, or a more irregular distribution shaped by recent mergers and interactions. At the epoch of interest, galaxy assembly is an ongoing process, and massive systems often show disturbed morphologies, tidal features, and multiple components, indicative of recent or continuing mergers. If TON 618 resides in such a context, its host could be the product of several earlier merging events, each bringing in new stars, gas, and dark matter, and contributing to the growth of the central black hole. The presence of an ultramassive black hole implies that large amounts of gas have reached the inner regions in the past, and much of that gas would have passed through the larger scale interstellar medium of the galaxy. As it cooled and condensed, some fraction formed stars building up the stellar mass while another fraction continued inward to feed the nucleus. Observational studies of quasar hosts at similar redshifts show a wide range of star formation properties, from systems with relatively modest activity to others with star formation rates of hundreds of solar masses per year. For a source as luminous as TON 618, many models favour a host with at least moderate to high star formation, sustained by the abundant gas supply funneled in from the circumgalactic medium and the cosmic web. Such a galaxy would contain large reservoirs of molecular gas in its inner regions, cold enough to collapse into new stars but also subject to heating turbulence and disruption from the energy output of the central active nucleus. Dust mixed with this gas would absorb part of the ultraviolet and optical light from young stars and from the nucleus re-radiating it in the infrared. As a result, the full spectral energy distribution of the host plus quasar would include substantial infrared emission, although separating the contributions of stars' dust and the active nucleus requires careful modelling. The stellar population itself would likely be a mixture of older and younger components, earlier episodes of star formation perhaps associated with the initial assembly of the galaxy, and with earlier mergers would have produced older stars that now populate the bulge and extended regions, while more recent bursts triggered by fresh gas inflows would add a younger population concentrated toward the inner kiloparsecs. This layered history would lead to gradients in colour and in chemical composition, with inner regions typically more metal-rich, due to repeated cycles of starbirth and supernova enrichment. In the case of TON 618, direct measurements of these gradients are not yet available, but the general reasoning that links black hole mass, host mass and environment suggests that its galaxy shares many of these characteristics. A further clue comes from the empirical relationships observed between the masses of central black holes and the properties of their host galaxy bulges in the nearby universe. Although these relations are best established for lower redshift systems, they imply that galaxies with very massive black holes also tend to have very massive stellar bulges. If similar trends hold at least approximately at redshift around 2, then the ultramassive black hole inferred for a TON 618 points toward a correspondingly large bulge mass. This does not fix a single value since the relation has scatter and may evolve with time, but it supports the view that the host is among the most massive galaxies present at that epoch. The dynamical structure of such a galaxy would reflect the combined gravity of stars' dark matter and gas. Stellar orbits in the inner regions might be largely random in direction, characteristic of a spheroidal component, while further out coherent rotation in a thick disk could help support the galaxy against collapse. Gas motions would be influenced both by these gravitational forces and by feedback from star formation, and from the active nucleus producing a complex velocity field with inflows along some directions and outflows along others. In optical and near-infrared light, the host galaxy's own emission is swamped by the quasar, but deeper imaging and spectroscopic observations, possibly with future instruments, may reveal more of its structure. For now, the host remains mostly an inferred presence, required by the need to house the central black hole, and to provide the gas supply that powers the luminous quasar, but largely hidden beneath the brightness of the nucleus. It is a massive evolving system that participates in the rich network of interactions at this cosmic time, drawing in matter from the halo and from companions forming stars and responding to the energetic influence of its central engine. TON 618 is classified as a radio-loud quasar, meaning that in addition to its intense optical and ultraviolet emission, it produces strong radiation at radio wavelengths that arises from relativistic particles moving in magnetic fields. This non-thermal radio emission does not come directly from the bright accretion disk, but from larger-scale structures powered by the central engine, most notably jets and lobes that carry energy away from the nucleus into the surrounding medium. In many radio-loud quasars, high-resolution images reveal narrow, elongated features that emerge from the central region and extend over distances of tens or hundreds of thousands of light-years, sometimes terminating in broader lobes where the jets interact with the external gas. Photon 618 current observations indicate powerful radio output, consistent with such a jet-dominated structure, although the extreme distance and limited angular resolution make it difficult to trace every detail. Even so, the picture supported by theory and by observations of similar systems provides a useful framework for understanding the radio properties of TON 618 in the context of its halo and circumgalactic environment. In this framework, relativistic jets are collimated outflows of plasma launched from very close to the central black hole and accretion system, then maintained over vast distances by magnetic fields and by the momentum of the flow. Once they leave the immediate nuclear region, they propagate through the interstellar medium of the host galaxy and then out into the circumgalactic medium. As they advance, they encounter gas at different densities and pressures, driving bow shocks into the external medium and forming internal shocks within the jet itself. Charged particles in these regions are accelerated to near light speed and then spiral around magnetic field lines emitting synchrotron radiation that spans a wide range of frequencies, including the radio band observed from Earth. Inside the host galaxy, the jets pass through a medium that can be dense and clumpy, with clouds of gas and pockets of hotter plasma. These inhomogeneities can deflect slow or distort the jets, leading to bends or asymmetries in their paths. Once the jets reach the outskirts of the galaxy and enter the circumgalactic medium, the density typically drops and the character of the interaction changes. The jets can expand more freely, and their leading edges may inflate large bubble-like lobes where the jet material accumulates after passing through a termination shock. In very powerful systems, these lobes can grow to sizes that rival or exceed the dimensions of the visible galaxy, creating radio structures that trace the energy output of the central engine on long timescales. For TON 618, such lobes would sit within the same extended halo that hosts the Lyman Alpha Nebula and circumgalactic gas, providing an additional channel through which energy and magnetic fields are deposited into the environment. As the jets plough through the medium, they heat and displace gas, carving out cavities and driving shocks that compress and stir the circumgalactic plasma. The lobes themselves, filled with relativistic particles and magnetic fields, have lower density than the external medium but higher pressure, so they can push outward, doing work on the surrounding gas as they expand. This process, often referred to as mechanical feedback, distributes a fraction of the quasar's energy output over large volumes, potentially slowing the rate at which gas can cool and fall back toward the center. In a system as luminous as TON 618, the energy carried by jets and lobes can be substantial, and even if only a modest fraction couples effectively to the gas, it can influence the thermal and dynamical state of the halo. Observations of radio-loud quasars at similar redshifts show evidence for such interactions, including cavities in hot gas and distortions in extended nebulae. While detailed maps of these effects around TON 618 remain limited, current knowledge supports the idea that its radio structures participate in similar processes. The orientation of the jets relative to the line of sight plays a key role in how the radio emission appears. If a jet points roughly toward the observer, relativistic beaming can boost its apparent brightness, while the counter-jet pointing away becomes fainter. If the jets lie closer to the plane of the sky, the two sides may appear more symmetric, highlighting the full extent of the lobes. For TON 618, constraints on this orientation are still loose, so discussions often adopt simple illustrative geometries rather than precise angles. Regardless of the exact alignment, the existence of strong radio emission implies that at least one relativistic outflow carries energy outward, linking the central regions to the larger scale environment. This spectral shape of the radio emission provides additional clues. Synchrotron radiation from a population of relativistic electrons naturally produces a power law radio spectrum with a slope that depends on the distribution of particle energies and on energy losses through radiation and expansion. In many radio-loud quasars, the spectrum is steep at high frequencies, indicating that higher energy electrons lose energy more rapidly, while flatter components can appear near the core where fresh particles are continuously injected. Beyond their immediate impact on the halo of TON 618, the radio jets and lobes also contribute to the wider intergalactic environment. As they expand and age, they can leak relativistic particles and magnetic fields into the surrounding space-seeding regions that may later collapse to form new structures or be illuminated by other sources. In this sense, the radio structures associated with ultra-luminous quasars serve as conduits through which energy and fields from the central engine permeate the cosmic web. Over timescales of tens to hundreds of millions of years, repeated episodes of jet activity can build up a complex pattern of radioplasma and enriched gas around massive halos. In the present view focused on the scale of the halo and its immediate surroundings, the radio properties of TON 618 provide another layer to the picture, already built from optical ultraviolet and Lyman alpha observations. The quasar is not only a bright point of light, but also a source of collimated outflows and extended radio structures that steadily reshape the medium through which they pass. As the narrative remains within this layer, it keeps attention on the jets and lobes and on their interaction with the host, galaxy, circumgalactic medium and larger halo, without yet moving inward to the smaller scale regions where emission lines broaden and accretion flows become more prominent. In the regions closer to the center of the host galaxy of TON 618, but still far outside the immediate neighborhood of the black hole, lies the extended narrow line region, a volume of ionized gas that responds to the quasar's radiation by emitting relatively narrow spectral lines. This gas occupies scales of hundreds to tens of thousands of light-years, overlapping partly with the inner circumgalactic medium and with the outer interstellar medium of the host galaxy. It is illuminated by the intense flux of ultraviolet and X-ray photons that stream outward from the nucleus, and in radio-loud quasars, it is often influenced dynamically by the passage of jets and by the expansion of radio lobes. The term narrow line refers not to the spatial extent of the emitting regions, but to the comparatively modest velocities of the gas compared with material closer to the black hole. Typical line widths in this region correspond to velocity dispersions of a few hundred kilometers per second, rather than the thousands of kilometers per second seen in the much more compact broadline region. These velocities arise from a combination of gravitational motions in the galactic potential and outflows driven by radiation and mechanical feedback from the nucleus. For TON 618, direct mapping of the narrow line region is limited by distance and angular resolution, but by analogy with similar quasars, and by interpretation of its spectrum, astronomers infer the presence of extended gas that acts as the main origin of strong narrow emission lines in the optical and ultraviolet bands. The narrow line region gas is clumpy with dense clouds and filaments embedded in a more diffuse ionized medium. Densities are lower than in classic star-forming regions, but higher than in the circumgalactic medium, placing this component in an intermediate regime where radiative processes are efficient and line emission can be strong. The composition of the gas reflects the chemical enrichment history of the host galaxy, with elements such as oxygen, nitrogen, carbon, and neon present in various ionization states. When hard radiation from the quasar penetrates these clouds, it strips electrons from atoms and ions and creates ions that produce forbidden and semi-forbidden emission lines when they de-excite. These lines are characteristic of active galactic nuclei and allow astronomers to distinguish quasar-powered emission from that produced by ordinary star-forming regions. In the spectrum of TON 618 strong high ionization narrow lines indicate that parts of the gas sight in regions with very intense radiation fields, at distances where the flux is still high, but densities are low enough that collisional de-excitation does not suppress the emission. The geometry of the narrow line region is thought to be anisotropic shaped, both by the distribution of gas in the host galaxy and by the pattern of radiation that escapes from the vicinity of the black hole. Dusty structures in the inner few parsecs can obscure the nucleus along some lines of sight, while leaving other directions more transparent. Along more open paths, ionizing radiation can travel outward in roughly conical beams illuminating gas over kiloparsec scales and producing extended emission line regions that trace these ionization cones. In TON 618, the exact geometry is not yet mapped, but it is reasonable to picture bright clouds and filaments wherever these beams encounter suitable gas and fainter regions in the shadows. Superposed on this radiative structure is the dynamical influence of outflows and jets. Where radio jets from TON 618 pass through the interstellar medium, they can compress clouds, shock heat them, or fragment them into smaller pieces. Shocks driven into the gas raise its temperature and can collisionally ionize atoms, adding another source of excitation. Downstream from such shocks, gas can cool and emit strong lines, sometimes with enhanced widths that reveal turbulent motions. Observations of other radio-loud quasars show elongated narrow line regions aligned roughly with the radio axis, suggesting that jets help to shape the distribution and kinematics of the line emitting gas. If similar processes operate in TON 618, then parts of its narrow line region may trace the paths where radioplasma and dense clouds meet. Velocities measured in narrow emission lines provide clues to gas motions in this zone. In addition to random motions and rotation in the galactic potential, many active nuclei show systematic blue shifts in certain high ionization lines that signal bulk outflows. For luminous quasars like TON 618, such blue-shifted lines are often interpreted as signatures of gas being accelerated outward by radiation pressure or by winds from regions closer to the nucleus. The speeds, typically a few hundred kilometers per second, are sufficient to lift gas out of the central parts of the galaxy and to transport metals into the halo, but often not high enough to unbind it completely from the galaxy's gravitational field. Another important aspect of the narrow line region is its role as a diagnostic tool. Because different emission lines respond to different combinations of ionization, parameter density and temperature line ratios can be used to infer physical conditions in the gas. Although specific measurements for TON 618 are limited, the general pattern of a powerful quasar with strong high ionization, narrow lines, points to a narrow line region that is highly ionized, moderately dense and extended over kiloparsec scales. This region forms an interface between the large-scale halo gas and the much more compact broad line and accretion structures nearer the black hole. In spatial terms, it occupies the inner parts of the host galaxy, overlapping with the stellar bulge and inner disk. In dynamical terms, it sits at the transition between gas, whose motions are dominated by the overall galaxy potential, and gas whose motions are increasingly influenced by the immediate gravity of the central mass. In this calm view, the extended narrow line region of TON 618 appears as a structured glowing volume of ionized gas, neither as diffuse as the circumgalactic medium, nor as extreme in velocity and density as the regions closer to the black hole. Clouds' filaments and shells move under the combined influence of gravity and feedback their emission lines, carrying information that links the bright nucleus to the broader galactic environment. Closer to the active nucleus of TON 618 lies the broad-line region, a zone of gas that moves at thousands of kilometers per second under the gravity of the central mass. In contrast to the more sedate motions in the narrow-line region, the clouds here orbit nearer to the black hole, at distances measured in light days to light months in many quasars, though, for an ultra-luminous system like TON 618, the characteristic radii are expected to be larger in proportion to its luminosity. Direct imaging of this region is far beyond the reach of current telescopes, so its properties are inferred from the shapes and strengths of emission lines in the spectrum. These broad lines, such as those of ionized carbon, magnesium, hydrogen, and other species, show widths corresponding to velocities of several thousand, up to perhaps tens of thousands of kilometers per second. The simplest interpretation is that the gas is bound to the central mass and moves in orbits or flows where gravity and motion are in rough balance. In this case, the line width provides a measure of the characteristic speed, and when combined with an estimate of the size of the region, yields an estimate of the mass of the central black hole. In many active galactic nuclei, the size of the broadline region is determined through methods that measure the time delay between fluctuations in the continuum, light from the inner accretion flow and the response of the broad emission lines. For TON 618, such detailed monitoring is more difficult, so astronomers rely on scaling relations that link line width and luminosity calibrated from nearer systems. These single-epoch methods involve uncertainties, and different lines and calibrations can give somewhat different results, but they broadly agree that the black hole in TON 618 lies in the ultramassive regime with a mass of many tens of billions of times the mass of the Sun. The gas in the broadline region is dense with number densities much higher than in the narrow-line region, so that many collisionally excited transitions are suppressed and permitted lines dominate the spectrum. Clouds or streams in this zone see an intense continuum radiation field from the inner accretion flow, rich in ultraviolet photons capable of ionizing a range of elements. As photons are absorbed and re-emitted, and as electrons recombine with ions, the gas produces a forest of emission features, each intrinsic line smeared into a wide profile, because the velocities span a broad distribution. The exact shape of a broad line depends on the geometry and kinematics of the emitting gas. A population of clouds in random orbits around the black hole can produce roughly symmetric profiles, while net inflows, outflows, or flattened rotating structures can imprint asymmetry, shifts, or double-peaked shapes. Some high ionization lines show systematic blue shifts, which suggests that part of the broadline gas participates in winds flowing outward from the inner regions. Lower ionization lines may instead trace gas that is more nearly in bound orbits, perhaps in a flattened distribution that connects gradually to the outer parts of the accretion flow. For TON 618 itself, the detailed geometry remains uncertain, but the presence of very broad lines with high equivalent widths places it in the class of broadline quasars. The physical origin of the broadline region is often discussed in terms of a clumpy medium rather than a smooth shell. Gas may condense into many discrete clouds embedded in a hotter, more tenuous phase, or it may form continuous turbulent streams and filaments. In either case, the emitting structures must survive for many orbital timescales, despite sheer radiation pressure and the threat of evaporation or disruption. Magnetic fields, radiation pressure, confinement, and continuous replenishment from larger scales have all been proposed as mechanisms that help maintain this region. For a system as luminous as TON 618 radiation forces can be strong, especially on dust and on ions with resonance lines. These forces can accelerate gas away from the midplane, contributing to the outflowing components of the broad line region and shaping its vertical and radial structure. At the same time, gravity from the central mass pulls gas inward, so that the broad line region represents a dynamic balance between in-full orbital motion and wind-like escape. Temperature in this region typically lies around tens of thousands of degrees high enough that hydrogen is largely ionized, and many metals are in intermediate ionization stages. The ionization structure is stratified with different lines, emerging preferentially from zones at different distances from the center, where the balance between ionizing flux and gas density changes. High ionization lines generally come from closer in where the radiation is harder and more intense, while low ionization lines arise farther out or in denser, more shielded clumps. For TON 618, detailed reconstructions of this structure remain challenging, but the overall pattern inferred from its spectrum is consistent with a luminous quasar with a broad line region that extends over many light days or light months. An important consequence of this structure is that the broad line region acts as both a sink and a mediator for material flowing toward the black hole. Gas that enters this zone from larger scales can lose energy and angular momentum through radiation collisions and interactions, with winds eventually settling closer to the midplane where it may join the accretion flow. Some fraction of the gas, however, is carried outward in winds or remains in long-lived orbits, continually reprocessing the radiation from the center into emission lines. Because of this, the broad line region both traces the gravitational influence of the central mass and participates in the regulation of how efficiently the black hole can be fed. In the calm view adopted here, the broad line region of TON 618 is a thick luminous shell of fast-moving gas, dense and structured, wrapped around the unseen accretion flow and black hole. Its broad lines provide one of the main observational windows into the dynamics of the inner parsec, and its existence allows astronomers to weigh the black hole even when it cannot be observed directly. Gas that reaches the broad line region of TON 618 has already come a long way inward, changing steadily as it moves deeper into the gravitational well of the host galaxy and its central black hole. Between the extended narrow line region and the innermost accretion structures lies a zone where the flow becomes more ordered and rotationally supported, forming the outer parts of the accretion system. Distances here are still large compared with the event horizon, but small compared with the overall galaxy, so the gravity of the central mass now dominates the motions of the gas. Material arriving in this region carries angular momentum, inherited from its previous orbits in the galaxy and from the geometry of inflows along filaments, bars and tidal features. To move further inward, it must lose part of this angular momentum, and the way that loss occurs sets the character of the outer accretion flow around TON 618. The gas that feeds this zone comes in several forms. Diffuse warm and hot interstellar gas can cool and sink toward the center, while denser clouds and streams are funneled inward by gravitational torques during interactions or mergers. On kiloparsec scales, non-axis symmetric structures transfer angular momentum from gas to stars and to the global pattern of the galaxy, allowing gas to drift inward over many orbits. By the time it reaches the inner few hundred parsecs, much of the random motion has been damped, and the gas has collected into a compact central reservoir. Although the structure of that region in TON 618 is not yet resolved, the behavior of similar quasars suggests that a substantial fraction of the cold gas in the inner galaxy participates in feeding the nucleus on these scales. Within this reservoir, the gravity of the black hole and the surrounding stellar bulge draws gas into a flattened configuration. The material settles into a rotating structure that bridges the interstellar medium of the host galaxy and the thinner disk found closer in. The outer parts of this structure are often described as a thick disk or torus, because the vertical height is a significant fraction of the radius. Turbulence, magnetic fields, and radiation pressure from the luminous inner regions puff the gas up, while radiative cooling and the tendency toward ordered rotation encourage it to flatten. Dust survives in these outer zones, so the gas is mixed with solid particles that absorb and scatter light and help in flowing material to radiate away energy as it spirals inward. As the gas orbits, it does not remain on fixed circular paths. Collisions between clouds, shocks, and magnetic stresses gradually redistribute angular momentum. In a magnetized, differentially rotating flow, small perturbations can grow into turbulence that act like an effective viscosity. The detailed microphysics remain an area of active research, but the broad outcome is that the outer accretion flow behaves as a slowly evolving viscous disk that can transport matter toward the center. Orbital periods in this zone are long compared with those near the innermost orbits. Over such timescales, fresh gas continues to arrive from the host galaxy, while some material is removed by winds launched from the disk surface or by feedback from any star formation that occurs within the dense gas. The balance between supply inward transport and losses determines how steadily the inner engine is fed. In a system as luminous as TON 618, the existence of a bright quasar phase implies that this balance has for at least some interval favoured a substantial net inflow with enough mass crossing each radius per year to sustain high accretion rates deeper in. Physical conditions in this outer flow differ from those in the broadline region even where their radii overlap. The broadline region is often modelled as clouds or streams exposed directly to the ionizing continuum, moving in complex orbits and producing very broad emission lines. The outer accretion flow, by contrast, is closer to a continuous medium with high column density and strong rotational support. Its surface layers, where radiation from the inner disk is absorbed and re-emitted, can contribute to some of the observed infrared and optical emission, but its main role is dynamical, providing a pathway for gas to reach smaller radii. Dust grains in the cooler parts absorb ultraviolet and optical photons and re-radiate the energy at infrared wavelengths, helping to build the broad infrared output of the quasar. As gas spirals inward, compression and viscous heating raise its temperature and dust gradually disappears as grains sublimate at smaller radii. The outer accretion flow around an ultramassive black hole must also remain broadly stable while handling large mass fluxes. For plausible conditions, models show that disks around black holes of many billions of solar masses can transport several solar masses per year inward without breaking apart globally. In the outermost parts of the flow, cooling can be efficient enough that the disk becomes gravitationally unstable. Self-gravity then produces spiral arms or clumps, and in some models these clumps can collapse to form stars. If similar processes occur around TON 618, part of the gas that enters the outer accretion flow may be converted into a compact ring of young stars before it can move inward. Feedback from those stars can stir the gas and alter the local balance between heating and cooling, but not all material is removed this way, and a significant fraction can continue inward and feed the regions closer to the black hole. Direct evidence for these detailed processes in TON 618 is limited by distance and resolution, but analogous active galaxies at lower redshift show many of the expected signatures, such as infrared emission from warm dust and molecular lines from cold gas in compact central disks. For TON 618, its enormous luminosity and spectral energy distribution point toward a similar configuration scaled up to match the mass of its central black hole. In this layer of the system, gas from kiloparsec scales has already lost much of its original angular momentum, yet still orbits at radii where periods are measured in thousands of years. Deeper inside the gravitational well of TON 618, the slowly evolving outer flow reshapes into a more organized accretion disk, a rotating structure where orbits become nearly circular and the transport of angular momentum proceeds through continuous stresses rather than through rare large collisions. In this region, the disk is often described as geometrically thin but optically thick, meaning that its vertical thickness is much smaller than its radius, while its density and opacity are high enough that photons generated within it scatter and are absorbed many times before escaping. Gas here moves in nearly Keplerian orbits, with the orbital speed set mainly by the mass of the central object and the distance from it. Closer in, the speed increases and the orbital period shortens, so the disk exhibits a radial gradient in dynamical timescales. The presence of even a small effective viscosity arising from turbulence and magnetic fields allows angular momentum to move outward through the disk. As a result, a slow but persistent drift of material inward accompanies a corresponding outward transport of angular momentum, maintaining a steady flow so long as the supply of gas from larger radii continues. The temperature within this outer accretion disk is not uniform. Energy is released as gas spirals inward, with gravitational potential energy turning into heat through viscous dissipation. In simple models, the rate of energy release per unit area decreases with radius, so the inner regions become hotter than the outer ones. Around a black hole, with a mass of many tens of billions of solar masses, the temperatures in the optical emitting zones can reach tens of thousands of degrees, while further out they fall to a few thousand degrees, allowing some atoms and even simple molecules to survive in the coolest parts. At the same time, the disk remains largely ionized in the regions that contribute strongly to the ultraviolet and optical continuum. Because the disk is optically thick, the emergent radiation approximates a superposition of many black-body-like spectra from different radii, each with its own characteristic temperature. When integrated over the whole surface, this multi-temperature structure produces a broad continuum rising from the infrared through the optical into the ultraviolet. In a luminous quasar like TON 618, the optical and ultraviolet part of this spectrum is often referred to as the big blue bump, widely interpreted as thermal emission from the accretion disk, with the outer disk supplying a large share of this light. Vertical structure in the disk adds another layer. Near the midplane densities are highest and temperatures somewhat lower, so the gas is relatively cool and dense. Moving upward, density falls and temperature rises, leading to a stratified atmosphere in which different heights contribute differently to the emergent spectrum. In some models, the upper layers of the disk are heated not only by local dissipation, but also by irradiation from closer in, creating a warm skin that can scatter and reprocess photons. For TON 618, the high luminosity of the inner regions means that irradiation likely plays a role in shaping the appearance of the outer disk, although direct constraints remain limited. Magnetic fields thread the disk and are amplified by differential rotation. The magnetorotational instability, a process in which small perturbations in a magnetized rotating flow grow and tap the free energy of shear, is thought to be a primary driver of turbulence and effective viscosity in many accreting systems. In the context of TON 618, this instability can stir the gas on a range of scales, creating tangled fields and turbulent motions that transport angular momentum. Even though the details of this turbulence cannot be resolved, theoretical models and simulations support this picture. Stability of the outer accretion disk is another key aspect. At large radii where the disk surface density is high and the temperature is relatively low, the self-gravity of the disk can become comparable to the tidal forces from the central black hole. In this regime, the disk can become gravitationally unstable, developing spiral structures or fragments. If such instabilities grow strong enough, they can lead to the formation of bound clumps, some of which may form stars within the disk. For a system like TON618 models suggest that beyond some characteristic radius, the outer disk may indeed enter this self-gravitating regime, so that star formation in the disk acts as another sink for gas and injects energy and metals back into the flow. This process can regulate the mass flow into the inner radii, preventing the disk from accumulating too much mass at large distances, although the extent and efficiency of such star formation remain uncertain and are inferred indirectly. Radiation pressure also influences the vertical and radial structure of the outer disk. In regions where the local radiation flux approaches a significant fraction of the level where it balances gravity, the disk can puff up, increasing its thickness. Dust opacity amplifies this effect in cooler zones, since dust grains are efficient at absorbing and scattering photons. As grains absorb radiation, they transfer momentum to the gas, which can help to lift material above the midplane, and may contribute to the launch of gentle disk winds. These outflows can remove angular momentum and mass from the surface, again affecting the net inflow rate. For TON618, the combination of thermal pressure, radiation pressure, and magnetic stresses shapes an outer disk that is not a perfectly thin static structure, but a slowly evolving flow. Observationally, the outer accretion disk of TON618 is not resolved directly, but its presence is inferred from the spectral energy distribution and from variability patterns in luminous quasars. Changes in the ultraviolet and optical continuum that propagate across wavelengths are consistent with a radially extended thermally emitting disk, responding to fluctuations in the mass accretion rate or in the inner radiation field. In this calm view, the outer accretion disk of TON618 is a broad rotating sheet of ionized gas cool enough in its farthest parts to harbour dust and perhaps star formation, yet hot enough closer in to radiate strongly in ultraviolet and optical light. Moving further inward toward the centre of TON618, the accretion flow becomes hotter, faster and more compact, and the relatively cool outer disk gives way to an inner region in which extreme gravity and intense radiation shape every aspect of the gas. Orbital speeds here rise to a substantial fraction of the speed of light, so that a parcel of gas can complete an orbit in days or even hours, rather than the thousands of years characteristic of the far outer flow. In these radii, viscous dissipation is very strong, and gravitational potential energy is released rapidly, driving temperatures in the optically thick disk up to values where most of the luminosity emerges in ultraviolet and soft X-ray bands. Although the disk remains broadly geometrically thin, in the sense that its thickness is smaller than its radius, the vertical structure is strongly affected by radiation pressure as well as by gas pressure and magnetic forces. For a quasar as luminous as TON618, the inner disk likely spends much of its time in a radiation pressure-dominated state, in which the pressure of trapped photons contributes significantly to supporting the gas against gravity. In this regime, the classical thin disk picture is modified by vertical expansion fluctuations and possible local instabilities, but the overall pattern of nearly circular differentially rotating orbits persists. Energy liberated by viscous stresses heats the gas, and this heat is carried outward by photons that scatter many times before escaping from the disk surface. The result is a bright multi-temperature continuum with the hottest inner annuli peaking at the shortest wavelengths and cooler zones emitting at longer wavelengths. Above and around this bright inner disk lies a still more energetic component, the corona. In this context, the corona is a region of very hot tenuous plasma, located either in a layer that sandwiches the disk or in more compact structures near the rotation axis. Electron temperatures in the corona reach hundreds of millions of degrees, far above those in the underlying disk. Soft ultraviolet photons rising from the disk surface enter this plasma and undergo inverse Compton scattering, in which each encounter with an energetic electron can boost a photon to higher energy. After multiple scatterings, a fraction of the disk photons are transformed into a power law spectrum of X-rays that extends to tens of kilo-electron volts. For TON 618 distance and limited photon counts make detailed X-ray spectroscopy challenging, but within current understanding its high energy output is naturally explained by a corona that is tightly coupled to the inner disk. The geometry of this corona is not directly imaged, so models explore several possibilities. One widely used picture places a compact centrally located source of hot plasma near the spin axis of the black hole, sometimes described as a lamppost geometry, from which X-rays irradiate the disk. Other models envision a more extended patchy layer of magnetically heated loops that rise above the disk surface at various radii. In either case, part of the coronal radiation escapes to infinity, while part illuminates the disk and is reprocessed. Photons that strike the dense disk can be absorbed and re-emitted or reflected, giving rise to spectral signatures such as broadened ion emission lines and a curved high-energy continuum. Because the inner disk orbits at relativistic speeds in a deep potential, these reflection features are subject to gravitational redshift and Doppler broadening, which smear them into asymmetric profiles. Even if individual features in TON 618 cannot yet be resolved with high precision, the general mechanism provides a coherent explanation for the presence of both thermal and non-thermal components in its spectrum. Magnetic fields are central to the existence and maintenance of the corona. The same magnetorotational instability that drives turbulence and angular momentum transport in the disk amplifies magnetic fields which then buoyantly rise into the upper layers. In these magnetically dominated regions, reconnection events can rapidly convert magnetic energy into heat-elevating electron temperatures and sustaining the high temperatures needed for efficient Compton upscattering. For TON 618, any short timescale fluctuations are smoothed by distance and limited photon statistics, but the underlying physical picture remains applicable. Radiation from the inner disk and corona also exerts pressure on gas above the disk, driving winds that emerge from a range of radii. In the inner regions where the radiation field is intense and the escape speed is high, line-driven and continuum-driven, winds can lift material off the disk surface, launching it into polar or equatorial outflows depending on geometry and opacity. These winds can carry mass angular momentum and energy outward, linking the innermost accretion zone to the broader environment. In some luminous quasars, signatures of such winds appear as broad absorption lines, or as blue-shifted emission components in high ionization lines. For TON 618, the detailed wind signatures remain under study, but the general expectation is that some form of disk-driven outflow accompanies the accretion, especially if the system accretes at a significant fraction of the rate where radiation pressure becomes dynamically important. Close to the black hole, general relativistic effects become progressively more significant. Light paths curve, time dilation alters the apparent rates of processes, and gravitational redshift subtly shifts the energy of photons emerging from the deepest parts of the potential well. Even at radii still several times larger than the event horizon, These effects can modify the observed spectrum, particularly in features that originate from the innermost disk, such as relativistically broadened iron lines. For an ultramassive black hole, the physical size of these regions is large in kilometers, yet small in angular terms given the great distance. So all of these relativistic signatures must be inferred from integrated spectra rather than direct imaging. In the calm, steady view taken here, the inner accretion disk and its corona in TON 618 form a tightly coupled system in which gravitational energy of infalling gas is converted into a broad continuum from the infrared to hard X-rays. The disk provides the dense, optically thick medium that radiates thermally, while the corona offers a hot, optically thin layer that processes part of this radiation into a high-energy tail. In the innermost parts of the accretion flow of TON 618, the orbital motion of gas is governed almost entirely by the curved spacetime close to the central mass, and classical pictures of orbits give way to relativistic ones. Here, circular paths exist only down to a certain limiting radius, the innermost stable circular orbit beyond which no steady circular motion is possible. Gas that reaches this radius can still move on nearly circular paths for a time, but any small disturbance tends to grow rather than damp, so the flow becomes marginally stable. Inside this boundary, orbits become dynamically unstable, and matter begins to spiral inward, rapidly, no longer able to maintain a long-lived ring. The exact location of the innermost stable circular orbit depends on the spin of the central black hole and on whether the disk rotates in the same direction as the spin or in the opposite direction. For a non-spinning case, the limiting orbit sits at a radius several times larger than the characteristic scale set by the mass, while for a rapidly spinning case with aligned rotation, the stable region can extend further inward, allowing gas to orbit closer before losing stability. In an ultramassive system like TON 618, the physical size of these radii is immense in kilometers, yet still tiny compared with the dimensions of the host galaxy, so that the relativistic region occupies only a minute fraction of the overall system while dominating its most energetic processes. Gas moving on orbits near this limiting radius does so at speeds that are a significant fraction of the speed of light. On the side of the disk where the motion carries material toward the observer, relativistic Doppler boosting makes the emission brighter and shifts it to slightly higher energies, while on the opposite side where the material moves away, the emission is dimmed and shifted to lower energies. At the same time, gravitational redshift causes photons climbing out of the deep potential well to lose energy, shifting their observed wavelengths. Light bending further modifies the appearance of the inner disk as photons emitted in directions that would not reach the observer in a flat space-time can be curved into the line of sight, and some photons that might have gone directly outward are instead bent back into the disk. The result is that the inner regions radiate in a way that is highly anisotropic in the local frame, yet after all relativistic effects are accounted for appear as characteristic broadened and skewed features in the integrated spectrum. In particular, spectral lines produced close to the limiting orbit can be broadened into wide symmetric profiles, with extended red wings that reflect the combination of high orbital speeds and strong gravitational redshift. Although direct high-resolution measurements of such lines in TON 618 are challenging because of its distance and brightness distribution, the general pattern seen in closer systems offers a template for interpreting any high-energy features that may be present. In the frame of the gas, the inner disk near the limiting orbit remains optically thick and radiatively efficient, continuing the trend from larger radii. Energy released by viscous stresses is radiated away rather than being carried inward with the flow, at least down to this transition radius. Because the binding energy per unit mass of an orbit increases, as the radius shrinks, each ring of gas closer to the center radiates more energy per unit mass accreted than rings farther out. The total radiative efficiency of the disk, meaning the fraction of the rest mass energy of accreting material that is converted into radiation before crossing inside the unstable region, depends on the spin and thus on the exact location of the limiting orbit. For slowly spinning cases it lies at modest fraction, while for rapidly spinning ones it can rise to values of order several tenths. Applied to an ultra-massive system like TON 618, even a modest efficiency implies that the observed luminosity corresponds to a mass inflow of several solar masses per year or more, highlighting how much material must pass through these innermost orbits over the lifetime of a bright phase. The motion of gas near the limiting orbit is not purely circular. Turbulence, magnetic fields, and pressure gradients introduce small deviations that can manifest as epicyclic oscillations, where fluid elements execute small radial and vertical motions superposed on their main orbital path. In a relativistic potential, the frequencies of these oscillations differ from the orbital frequency and from each other, and they vary with radius. Theoretical models suggest that resonances between these frequencies, or between them and variations in the accretion rate, can produce characteristic patterns in the emitted light, such as quasi-periodic oscillations at specific timescales. In stellar mass black hole systems, some of these patterns have been observed, offering insight into the structure of the innermost flow. For TON 618, the much longer characteristic timescales and greater distance make direct detection of such rapid variability extremely difficult, but the same underlying physics is expected to shape the dynamics of its inner disk. Magnetic fields in this region remain crucial both for transporting angular momentum and for linking the disk to the corona and to any larger scale outflows. Field lines anchored in the differentially rotating disk can wind up and reconnect, releasing energy and contributing to the heating of the overlying hot plasma. They can also help to collimate any emerging jets by providing a channel along which plasma can be accelerated outward. At radii near the limiting orbit, the interplay between rotation gravity and magnetic tension is at its most intense, with small changes in conditions potentially leading to changes in the structure of the corona or the strength of any outflows. Despite these complexities, the overall flow pattern in the innermost stable region maintains a simple radial progression. Gas at slightly larger radii slowly drifts inward through the disk, crossing one annulus after another as angular momentum is transported outward. When it reaches the limiting radius, the character of its motion changes. It can no longer find a stable circular path, so it begins to spiral inward, more rapidly transitioning from a slowly drifting orbit to a plunging trajectory. In many models, little additional radiation is produced during this plunge because the gas has little time to interact and to dissipate energy before moving deeper into the gravitational field. Thus, the region just outside the limiting orbit acts as the main radiating surface of the accretion flow, while the space interior to it, though dynamically important, contributes less to the observed luminosity. In summary, the relativistic innermost orbits around TON 618 represent a narrow but critical zone where the smooth luminous disk comes closest to the central mass, while still maintaining approximate circular motion. In this region, orbital velocities are very high gravitational redshift, and light bending are strong, and the balance between radiation magnetic forces and gravity reaches its most delicate point. The emission from here shapes the high-energy continuum and any broadened line features, and the dynamics here determine how efficiently mass and energy are transferred from the accretion flow into radiation setting, the stage for whatever processes operate deeper within the gravitational well. At the centre of TON 618 lies the object that organises all of the surrounding structure, an ultra-massive black hole whose gravity governs the motion of gas and stars from the innermost orbits of the accretion disk to much of the inner host galaxy. The black hole itself emits no light from within its event horizon, yet its presence is revealed by the energy released as matter falls toward it, and by the speeds attained by gas close to the centre. In TON 618, the combination of broad emission line widths and luminosity-based size, estimates for the broad line region points to a central mass of many tens of billions of times the mass of the Sun. Different methods and calibrations produce somewhat different numerical values, so astronomers treat the derived mass as a range rather than a single exact figure, but all approaches agree that the mass is extreme, placing this black hole among the most massive reliably inferred in the observable universe. From this mass, one infers the characteristic size of the event horizon, the boundary beyond which not even light can escape. For a black hole with many tens of billions of solar masses, this horizon radius is measured in tens of billions of kilometers, a scale comparable to the planetary region of a solar-type system, yet concentrated into a volume from which no signal can emerge once it crosses the boundary. In the simplest non-rotating case, this radius defines a sphere, while in more realistic spinning cases the horizon is slightly flattened, and the surrounding space-time acquires additional structure, but the essential idea of a closed surface from which light cannot escape remains. In the accretion picture for TON 618, the luminous disk and corona extend down to radii of a few times this horizon size, with the innermost stable circular orbit setting the inner edge of efficient emission. Inside that orbit, gas plunges inward and crosses the horizon in a time that is short compared with the timescales of disk evolution, and once inside it no longer participates in any process that can send information outward. The connection between mass and luminosity leads to the idea of a characteristic limiting brightness set by the balance between radiation pushing outward and gravity pulling inward on ionized gas. When the outward force of radiation on electrons communicated to ions through electric forces becomes comparable to the inward gravitational attraction, the inflow can be driven into strong outflows. This limiting luminosity scales with mass so that more massive black holes can in principle shine more brightly without unbinding the inflowing gas. For TON 618, the observed luminosity is high enough that it lies at a substantial fraction of this characteristic level, if standard assumptions about the efficiency of accretion hold. In simple terms, the quasar radiates strongly, but not in a way that demands extreme departures from known physics. The mass and horizon scale also fix characteristic dynamical times near the centre. Orbital periods at radii of a few times the horizon scale decrease as the radius shrinks and are set by gravity in curved space-time. For an ultramassive black hole, these periods can still be as short as days or weeks in the innermost stable orbits, even though the physical size is large because the gravitational field is strong. Although practical limits make the detection of very short timescale changes difficult in TON 618, the underlying characteristic times remain set by the mass and spin. Another consequence of the extreme mass is the depth of the gravitational potential, well carved out at the centre of the host galaxy. Stars and gas within a certain radius feel a gravitational field dominated by the black hole, rather than by the distributed mass of stars and dark matter, and for an object of tens of billions of solar masses, this sphere of influence can extend over hundreds to thousands of light-years. Within this region, stellar orbits and gas dynamics are strongly affected by the central mass, and any star that ventures too close can be tidally disrupted, its material added to the wider reservoir of gas near the nucleus. The event horizon itself remains a purely gravitational boundary, not a material surface. Gas and radiation that approach it experience increasing redshift, so that photons emitted closer and closer to the horizon arrive with lower energies and appear delayed to a distant observer. In practice, most of the radiation that defines the appearance of TON 618 originates from regions a few to several times farther out than the horizon, where the disk and corona still radiate efficiently. The horizon is therefore best thought of as a silent interior boundary that removes mass and energy from the observable universe without adding its own light. Nevertheless, its existence sets the fundamental scale for all inner processes, fixing the conversion between mass and gravitational radius, and anchoring the structure of the spacetime in which the disk corona and innermost orbits reside. Measurements of the mass of TON 618 also inform broader questions about the growth of such black holes in a relatively young universe. To reach tens of billions of solar masses by the cosmic time corresponding to a redshift of about 2.2 requires prolonged accretion episodes of rapid growth mergers with other black holes, or some combination of these processes, each limited by radiation pressure and by the supply of gas in the host halo. When astronomers compare the inferred mass of TON 618 with models of black hole evolution, they find that its existence is demanding, but still compatible with scenarios that allow for sustained efficient accretion in dense environments. The key point is that the central mass and its associated horizon in TON 618 are large enough that the surrounding structures from the innermost orbits through the disk and out to the broad and narrow line regions can all be organized by its gravity, while radiating with a power that approaches, but likely does not greatly exceed the level at which radiation and gravity come into balance. Immediately outside the event horizon of TON 618 in the region, where gas completes its final orbits and begins its inward plunge, the energy released by accretion couples back into the surrounding medium in several connected ways. Radiation from the inner disk and corona streams outward in all directions, though shaped by the geometry of the disk and by anisotropies in the coronal emission. Part of this radiation escapes directly to intergalactic space, while part is intercepted by gas in the immediate vicinity, depositing energy and momentum. At the same time, magnetic fields anchored in the rapidly rotating inner disk and threading the plasma near the black hole channel some of the gravitational energy into collimated outflows and broader winds. In this compact zone, only a few tens of gravitational radii across the processes that convert in falling matter into outgoing radiation particles and fields reach their greatest intensity, and the balance between them sets the conditions under which TON 618 interacts with its closest gaseous surroundings. The intense radiation field close to the black hole exerts pressure on electrons in the ionized gas. This radiation pressure acts against gravity and can lift material away from the disk surface where the opacities are high, especially in regions where line absorption by partially ionized metals enhances the coupling between light and matter. In such zones, line-driven winds arise in which gas is accelerated to high speeds as it absorbs and re-emits photons from the bright continuum. The velocities in these inner winds can reach thousands of kilometers per second, comparable to the speeds in the broad line region. Some of this outflowing material may remain relatively dense and cool enough to contribute to broad absorption and emission features at high ionization, while other parts become hotter and more tenuous as they expand. Along with radiation pressure, thermal driving contributes to these winds. Gas that is heated strongly by X-rays in the inner regions can reach temperatures at which its thermal speed becomes a significant fraction of the escape speed. When this occurs in the upper layers of the disk atmosphere, pressure gradients drive material outward, producing a thermally driven wind that emerges from a range of radii. This component can blend with line-driven flows, creating a pattern of outflow that depends on the spectral shape and luminosity of the central source, as well as on the distribution of gas and dust. In a system as bright as TON 618, the integrated effect is expected to be a substantial mass loss from the inner disk regions, with some fraction of the accreting material diverted into winds rather than continuing all the way to the horizon. Magnetic fields add another channel for feedback. In the immediate vicinity of the black hole, strong ordered fields can tap the rotational energy of the disk, and if the black hole itself is spinning the rotational energy of the space-time near the horizon. Under suitable conditions, magnetically dominated structures extract energy and angular momentum and feed it into relativistic jets. In TON 618, the presence of powerful radio emission points towards such a magnetic link between the innermost plasma and the large-scale jets and lobes described in earlier sections. Close to the black hole, these fields help to collimate the outflow, shaping it into narrow beams that emerge along the rotation axis. As the jets propagate outward, they carry away particles, fields, and angular momentum, retaining a memory of their origin in the inner few tens of gravitational radii. The combined action of radiation, winds, and jets determines how much of the gravitational energy released near the horizon emerges as light versus mechanical and magnetic power. Estimates based on the luminosity of TON 618 and on standard accretion models suggest that a large fraction of the available energy appears as electromagnetic radiation from the disk and corona, while another fraction is carried outward mechanically in outflows and jets. On small spatial scales, feedback from the inner engine affects the structure of the inner disk. Radiation pressure puffs up sections of the disk, altering its vertical thickness and changing the way it intercepts and reprocesses coronal emission. Winds that remove mass and angular momentum from the surface of the disk influence the local accretion rate at slightly larger radii, creating couplings between conditions near the horizon and those farther out. Magnetic stresses that launch jets also modify the torque distribution within the disk, changing the rate at which angular momentum is transported, and therefore the rate at which mass flows inward. Over many orbits, the cumulative effect of these processes shapes the structure of the accretion flow and the pattern of energy release. On somewhat larger scales, still within the inner parsec, the energy carried by winds and radiation begins to interact more strongly with the surrounding gas. Dense clouds that wander into the polar regions close to the rotation axis can be ablated or accelerated by radiation and by the edges of the jets, while material in the equatorial plane experiences a combination of radiation pressure and thermal heating. Over time, this can clear low-density funnels along some directions, while leaving denser, more obscuring structures in others. Such anisotropy in gas distribution and in the escape of radiation is a common feature of luminous active nuclei and helps to explain why quasars with similar intrinsic properties can present different appearances depending on orientation and on the structure of the inner few parsecs. For TON 618, the immediate surroundings of the black hole likely include both channels that allow relatively direct escape of radiation and outflows, and regions where gas and dust remain dense enough to absorb and re-emit a substantial fraction of the inner luminosity. In this final inner layer of the exploration, the focus remains on the immediate neighborhood of the event horizon, where the flow of gas transitions from orbiting matter to plunging trajectories where radiation pressure, magnetic forces, and gravity compete and combine, and where the energy that powers the visible quasar is first divided among light winds and jets, before propagating outward to larger scales already described in earlier sections.